Recording is on.
So stage,
Okay, thanks for
the
the
floor is yours. Yes, please.
yeah. Make a simple question. I haven't published a paper on SIGCOMM yet, so I'm still working on
Okay,
it.
so submit. Okay, yeah.
Let me share my screen.
Mm.
Yes. I guess I already shared the screen.
Yes.
I hope I see it clearly. And so, hi everyone, I'm happy to introduce here about my work, which is in network machine learning on programmable network devices. And this is mainly my PhD project, and it mainly covers what I've done in the past 4 years. And just please interrupt me if there's any questions or any point that would like to further discuss. So let me start. The first is what is the beginning of program. The project comes with the programmable switches, or in other words, the programmable network devices. And at the very beginning, the switches, typically switches, are used to be fixed functional. And everyone need to run the same protocol for the internet to work. Well, in the early decades, the cloud providers want to run their own protocol within their data centers, and they want to modify the existing protocols to meet their own service. And they don't want to share these protocols with others in order to gain profit. So to meet these requirements and needs, the network equipment providers begins to become programmable. And the simplified the programmable packet processing pipeline can be summarized as here. It begins with a programmable parser mainly used to extract feature from the headers, and which means what are the headers in the packet looks like, and what are the informations in this header. And after that, it is connected to a programmable migration pipeline, and is mainly in charge of the processing algorithms based on the extracted features from the packet header. And after this pipeline, it is connected to the deparser, where it put back all the headers to the payload and send the packet out. So which means it is what should the output packet looks like. And with the help of the programmable network devices, there is a new direction, emergence, which is in network computing. So it means the execution of native host applications within the network using the standard network devices like programmable switches. And the typical target of in-network computing, or the typical target platforms, including high-end switch ASICs like Tofino switch, and some middle-end devices like DPUs, SmartNICs, and FPGAs. And for the switches, they are typically able to reach terabits per second. And for the DPUs, SmartNICs, and FPGAs, they are able to process around 400, 800 Gbps packets. And it even have some low-end devices like Raspberry Pi, and it mainly can be used for the IoT environment and for education. And some typical in-network computing applications are related to network functions and acceleration services, like caching, such as key value store, the security applications like do the DDoS detection and mitigation, some distributed systems like consensus, and the database acceleration, and it can even be used to control the industrial robotic arms. And why we try to explore in-network computing is because its performance benefits. The study find that in-network computing is able to help us to reduce 10 to 100 times latency and to gain 10,000 times improvement in throughput, and also around 1,000 times improvement in power efficiency. So this means that we can use a single switch to replace several racks of servers, so which is a huge benefit. And then the in-network machine learning comes. The idea is very similar to in-network computing. So it means what we want to do is offload the machine learning inference process from the servers to the network devices, which becomes in-network machine learning. And in-network machine learning is a type of resource-constrained machine learning. And unlike other resource-constrained machine learning, you can't just compile the code and run it on a network device, as its architecture, the piece architecture of this network device are very different from a CPU or a GPU. Let me further compare the server-based machine learning and in-network machine learning. So in-network machine learning runs on the network infrastructures instead of the local PC or servers. And this is about location. And for this device, it mainly have a PISA architecture, and it can be some ASICs, the FPGAs, but all with the PISA architecture, which is very different from a CPU or a GPU. And the language used to programming these devices, which is P4, instead of server-based machine learning using C, Python, or MATLAB. And the manner of in-network machine learning is also different, and mainly employs the offline training, and then map the model to the device to do the online inference. And after talking about difference, realizing in-network machine learning is not an easy task. It mainly because of the limited resources on this device, which is very limited compared to a server or a PC. For example, it have limited mathematical operations, so which means the multiplication and division operations are not supported. It have limited memory, only around tens of megabits, and it have limited data types. For example, floating point numbers are not supported. And it also have limited stages, so this means for loops are not supported. So what we want to do is to overcome these limitations and realize the machine learning models on this device. And the motivations of realizing in-network machine learning can be summarized into the 3 L's. And the first L is about the location. Because these programmable network devices are along the data path, the packets need to be processed by the servers have already been processed by this device before they reaching the servers. So allowing these devices along the data path to support inference is a natural step. Besides, the network devices are at the data aggregation point. It have a better view compared to the servers or the PCs. And also, these devices are already exist inside the network, so we do not need to spend money or have extra expenditure to buy further accelerators to process these machine learning inference tasks. The second L is latency. So processing machine learning inference on a network device will always have lower latency than processing in the cloud, since it can terminating data and return it along its data path. So which means that in-network machine learning have a lower data path, can reduce several hops. So the latency can be reduced. And the last L is related to the load. The network devices are designed, as I introduced before, which is high throughput packet processing and forwarding. And in-network machine learning runs on it, naturally will have a good system performance. And also, if we can do the machine learning task close to the data source and terminating the data early along the data path, which means that we can reduce the amount of traffic flowing to the server and reduce the backend load. So given these motivations, there are already prior works on in-network machine learning, but most of these works focused on deploy a single model on a network device, on a single network device. Well, in-network machine learning still needs diverse algorithm mappings, so which means that we need a generalized mapping methodology to realize a wide range of machine learning models. And these models should fit within the unmodified commodity hardware, like the Tofino switch. And to deal with this challenge, I introduced 3 mapping methodologies. And the first one is the direct mapping. It mainly targets at the algorithm have a series of sequential operations, which should be similar to the pizza architecture. And for example, the decision tree, and also some algorithms like a binarized neural network. And the second methodology is encode-based. And this methodology is targeting on the algorithms that can be summarized or abstracted as a slicing of the feature space. And for example, the k-means and the random forest. And the last methodology is a lookup-based, and it mainly targeting algorithms that can be treated as a series of polynomials. And it mainly use lookup tables to replace the operations and to store the intermediate results in these polynomials. And this methodology mainly targeting on the algorithms like the support vector machine, naive Bayes, and k-nearest neighbors. Well, with the help of these methodologies, we are able to map about a dozen different machine learning models with 50 plus different variations. And the model mappings are not enough. There also needs to be a rapid prototyping solutions, and the solution need to support easy configuration and modification of deployed models, and the easy migration among platforms and the use cases. To further explain this point, these two figures mainly shows the line of code that requires to change if we change a single parameter on a model. And we can see both the data plane P4 code and control plane code requires tens to hundreds of lines of code with this single change. So this means that we need a framework to help us to automate all the process. So to deal with this, I introduced Planter. So Planter can help us to take a use case from a data set all the way to a deployment on a target with a single click. So given this data set, Planter first trains the machine learning model using standard libraries like scikit-learn or PyTorch. And its front end enables parameter selection and auto-tuning. The trained machine learning model is then mapped to the P4-based data plane code and the control plane code typically in Python and P4 runtime. The planter will also auto-generate the bash scripts and code for testing. After generate this, the planter will activate the generated bash scripts to compile the P4 code, to load the model to the target, and test it. So planter is a modular framework, which means that user can select the required model, the needed architecture, the targets, use cases, and planter will take all these parts and generate the P4 code and control plane code for the deployment. And also because of the with the help of the planter, the user with no machine learning background or have not familiar with the P4 programming can easily realize in-network machine learning in their research. And also with the modular framework design, if there is a new model emerging or there is a new network device are released, we can easily support it by adding a new module. And previous slides, we mainly introduced how we map the model and how we can easily deploy these models or one of these models on a single network device. We now need to extend it to deployment scenarios. And the first one I would like to introduce is a hybrid deployment. The hybrid deployment is what we learn from the heterogeneous computing. So what we do is we deploy a small model on a network device, for example, a switch, which is responsible for high throughput and low latency processing with reasonable machine learning inference performance or inference accuracy. The large machine learning model is deployed at the backend for the high precision machine learning inference. So we use the classification confidence to decide if the traffic need or the decision can be made on a network device or need further process by the backend. So for the normal for the traditional scenario, when normal traffic combined with the malicious traffic coming in the network, it will firstly forward it by a switch to the backend server, where racks of machine learning servers are used to process them and to drop the malicious traffic. And with the help of hybrid deployed in-network machine learning, when packets coming inside the network, it will firstly processed and classified on the switch. And for those classified as malicious and the decision have a high confidence, this traffic will be dropped immediately. And for those classified as normal and have high confidence, it will directly goes inside the network and bypass the inference servers. And only those have low confidence decisions will be forwarded to this backend for further process. So this is able to help us to significantly reduce the backend load. So this figure mainly shows how we evaluate our hybrid deployment on anomaly detection use case. And we can see that the whole system is able to achieve close to baseline machine learning inference accuracy, and at the same time reduce the backend load by about 70%. So this means the hybrid deployment is able to allow us to realize the in-network machine learning system that balance the system performance and inference accuracy. Well, the hybrid deployment is not enough, because in hybrid deployment, we still only deploy a single small model on a switch. And since the switch have a constrained resources, we cannot scale the small model unlimitedly. And the inference accuracy of this small model will also influence the inference performance of the whole system, and further influence, because it also will influence its decision confidence, and thus further influence the system performance, like the portion of traffic need to be processed by the backend server. So what we want to do is, if there is a solution that can allow us to further scale the in-network model. So what we propose is a distributed deployment. So which means that we want to use the unused resource, jointly use the unused resources on different programmable network devices, and to deploy a larger machine learning model inside the network. So the problem is the limited scalability of in-network computing. And to further explain it, we can see that the network device can realize network functions with spare resources. And it can also realize the in-network machine learning model within it. Well, if we want to jointly realize the network functions and large in-network machine learning model, for most cases, it will run out of resources. And this figure mainly shows the resource consumption of a real router on a two-funnel switch. And we can see around 2/3 of the pipeline stages, its resources are partially used. And for the 1/3 of the pipeline stages, its resources are totally unused. And what we want to do is to use these unused resources jointly among the network to able to deploy, in order to deploy a larger in-network computing algorithm. And this computing algorithm definitely includes the machine learning algorithm. And in order to realize the distributed in-network computing, the first challenge is how we can realize without affecting the existing network functions. And for example, when traffic going through the network, we should not determine what are the next hop, or what should be the routing. We should allow the network, the normal network functions, to deal with the multipath and deal with the load balancing. So to realize this, what we do is we design a ILP planner to deploy full functionality of the computing algorithms along all the paths. And firstly, to realize this ILP planner, I define several constraints. And the first is about dependency. So which means that for any segments, all its preceding segments should appear at least once before it on any path. So this is make sure that the order of the segments are correct. And the second constraint is about integrity. So which means that for any path, all the segments should appear at least for one time. And the last constraint is about resource. And it means that for any node, the resource consumption should be below the total available resources on the network device. And these constraints can be converted into the equation as shown here. And besides the constraints, we also define several objectives, like the resource objective function, which is used to minimize the resource consumption, and the latency function is used to minimize the latency. And then we also have an optimization function, which is a weighted sum of all these objective functions. And these objectives can be converted to the equation shown here. And after this, we also have another challenge, which is about information sharing across these distributed segments. And to deal with this, I designed a DINK header. And this header is used to pass intermediate results across the segments, and it is transparent to the user. So which means that when packet coming into the network, the header is automatically added and used to pass information. And before the packet is going out of the network, the header will be automatically removed. And inside the header, we have a intermediate features field, which is used to pass the information. And we also have a bitmaps field, which is used to identify which segments has been executed to make sure that segments are executed in order. And after this, we also need an easy-to-use framework to help us to automate everything. So we also propose a DINK framework, which use the network operator provided network information and the user provided computing algorithm with annotations as the input. And with these inputs, the framework will firstly pass the DINK splitter module, and which splits the input in network computing algorithm based on the user annotations. And it will also auto-generate the DAG of the network topology and also generate the DAG for the in-network computing algorithm. And with these inputs and these DAGs, and also the predefined constraints and objective functions, the DINK planner module will help to auto-generate the deployment strategy or the planning of the segments. And based on these planning results, the framework will automatically generate the P4 code or the data plan code for all the network devices inside the network. And then the framework will, similar to the planner, will auto compile the generate code, load the model to the network, and do the test. And the DINK framework is similar to planner, it's an automated framework. And it is also have a modular design, which means if we have a new planner model, that we can easily replace it with a new planner module. And we evaluate the DINK on two topologies. One is a cloud data center topology with 33 nodes. And another one is a British Telecom network topology, which is a wide area network backbone topology, which is around 1,000 nodes. And its physical location on the map is shown here. And for the anomaly detection use case, we can see for most of the machine learning functions, although they are able to deploy alone on a single network device, when it coexists with real router, most cases they are run out of resources. And with the help of DINK, all of these models are able to distribute it deployed on both topology and coexist with the network function. And we also evaluate the throughput of all the segments when it coexist with the network function, and we can see all of them are able to achieve full line rate, which is 6.4 terabytes per second. And we also compare our proposed DINK with the SOTA, which is a flat plan. And we can see for the number of nodes used to deploy the the random forest algorithm, on the cloud, which is a relatively symmetric topology, the DINK requires the same percentage of nodes as flat plan to deploy the algorithm, while on the asymmetric, more complex BT topology, DINC is able to reduce around 60% of nodes used to realize the random forest. And in terms of the number of hops used to finish the computing, and the DINC and flat plan have shared the same performance. And in terms of the number of duplications of nodes, duplication of segments used to realize the random forest, the DINC is able to reduce around 35% of duplications on closed topology and around 80% of duplications in BT topology. So which means that the proposed DINC IOP-based planner is highly efficient. And besides the distributed deployment, we also support several different deployment strategies like the federated deployment, which can deploy separate models on different regions that are highly privacy sensitive and don't want to share their raw data or training data with each other. And this can be applied to privacy sensitive use cases. And early adopters has already applied our in-network machine learning mappings, the frameworks, and deployment strategies to a range of use cases. And for example, for the finance-related applications like predicting future stock price movement and transaction fraud detection. And for the network functions, which they use Q-learning for load balancing, in-network Q-learning for load balancing. And on IoT use case, they use in-network machine learning for traffic classification. And also for cybersecurity applications, which include e-commerce bot traffic detection and smart grid force data injection detection. And be sure that there are many more applications to explore. Until now, we already have several publications that related to in-network machine learning, and we also release multiple artifacts, which is open sourced, that can help us to easily realize in-network machine learning in their use case. So to summarize, in order to deploy efficient in-network, in order to deploy machine learning models, we can use the mapping methodologies to efficiently map the trained machine learning model to the data plane. And we also design a modular in-network machine learning implementation framework. And we also provided a high-performance hybrid in-network machine learning system that can balance the inference accuracy and system performance, like the high throughput and low latency. And to overcome the resource barrier of programmable network devices, we can use the distributed deployment, which is the DINC framework. And we also already apply in-network machine learning to different use cases. And there are many more applications and use cases to explore. And with that, I'm happy to take your questions.
Yes, thank you very much, Changgang. It was very exciting presentations. So if there is any question, so I have actually a couple of questions, so but I don't know if there is any questions.
Yeah.
Okay, so Zain.
Yeah, hi. How do we use this planter from open source GitHub project? Because I was looking into the paper planter seeding trees within switches, and is there? Can I just
Yes.
clone the repository and get started? Do I need, or is it like hardware specific? I need to be on a specific server hardware that I have to reciprocate that.
Well, the Planter supports, the first thing is that Planter has already been open source, so you can easily find Planter under this organization, repository organization, and you can also find all other open source artifacts under this link. And for the second is for Planter, it supports several different deployment targets. So which means that it not only supports the commodity hardware that you need to purchase, it also supports software targets like BMV2 that you can easily implement on a Linux server. So you can try it easily
Yeah, I
without
see.
purchasing some high-end devices.
Yeah, got it.
And also I have like a small demo. I hope it can able to run. So this is Planter. So let me to make it slower. So it's too fast. So what you can see that after you activate Planter, it will automatically load the configurations that in a configuration file. And if you are not sure about what configuration to input, or you can just leave it as blank, then the CLI will just stop and to guide you to do this input. So for example here, which means that there is a missing configuration and just stop here, and you can just input like the number of trees that you want to use. And then it will just automatically train the model and convert it. So here is already the conversion process. So we'll convert the trained model into the P4 code and table entries and also the control plan code. And then you can see after it generate everything, it will just compile the code and load the model to the target and do the test. So here is already, you can see it load the model to the BMA2 model and already load the table entries. Yes, and
See.
it stopped it, and it can also support something like automatically sending and receiving packets to verify it. But because of this verification, the parameter that I select is simply compile and deploy. So it do not send and receive packets to do the verification. So probably I also have probably have a user. So probably I can just, if I have that, I can show a little bit. So this is how Planter works. It have a detailed like explanation to each step of the Planter, the workflow. It will firstly train the model and convert the model and do the test. And inside the Planter repository, you can easily find there is a Planter user manual. And inside that user manual, it will detailed explain all the steps in the Planter and also all the modules that's supported by Planter. So you can simply use the menu to select the model that you want to use, select the target or the use case that you want to use.
See.
Yeah.
So I have some questions actually. I will jump in. So actually, Changgang, I remember that actually. So we tried to basically implement this one on the SmartNIC. So today I see that you more focus on the like switch as a target.
Yes.
So if you want to, but also I see that in the list of the target you had already also Alveo FPGA for that. I think
Yes.
maybe that one also interested for people who wanted to have P4 on the FPGA. But then among these smart NICs that already existed, so which one you recommend more for P4 based implementation? I mean, like for example, like AMD Pensando or like this
Yes.
Bluefield, because I remember that. So when we met and we were working. So we tried to have like a software switch, and then we have the software switch that it support the P4. But then it is also
Yes.
latency wise is not good. So what do you recommend for like having the P4 on the smartphone?
And for the in-network machine learning, I think nowadays for the NIC or the smart NIC or the DPU, I think for those that have native support of P4 will be a preferred target. For example, the DPU and the Pensando of
Yeah.
the
Mhm.
which natively support P4, and also Intel IPU it also support P4.
Okay.
Well, for the Bluefield and the future Connect X8, well, the architecture is a slight different. So, for example, for the Bluefield 3, we can treat it as a it have a NIC subsystem, and it have an ARM core.
Yes.
So inside the NIC subsystem, it have two programmable components, which is a hardware or programmable hardware switch. It's a E switch, which can be configured through the host or ARM interface. Well, it's not P4 based, and it also have a RISC-V core, which is DPA. Well, it's also programmed by C programming language, and its processing capability is to some extent limited. Although it's able to reach full line rate, but you can't run the very complex algorithm on them. So if we want to realize in-network machine learning on this type of device, and also future Connect X8 because it also have a DPA and a E-switch, probably we need some modification to the mappings and also need some modifications to the framework to allow it to support the C programming and to support the specific C programming style of the DPA or the E-switch.
Yes.
So
Also, in this Bluefield, I heard about the DPL. So apart from DPA, that it is programmed by like a C programming, so for packet processing. Also, I don't know, you heard about also DPL. So this is like a P4, like a processing of the. But I think it still is a kind of like a mimicking. It's not like a native hardware, but it's a DPL.
uh, I'm not that very familiar with that. I think from some resources, I heard that Bluefield 3 have some plan to support P4, but so far there is not
So,
sufficient materials for that,
so
I
your
guess.
recommendation is more like a AMD Pensando for like having the
Yeah,
DPL.
it will be more easy to realize
Yeah.
with native P4 support. But if you're very familiar with the mapping, then you can easily use other, because the idea of in-network machine learning is not the must of stick to P4. If you can realize the program inside the data plane, even use C is also a good idea. So,
Mm.
and I think the mapping idea is also similar. So if you can convert the complex algorithm with match action table entries or with a series of concatenate match actions, its performance will be good.
Even like a video DPA. I'm just like even.
Yeah, on TPA, so you can just if the table entries are not very large,
Oh yeah. Okay.
then it's also not a bad idea.
Yeah. Okay. Good. But are you also like a fan of, for example, like implementing machine learning directly on ARM cores? Do you think that would be, how is it like if you compare?
Oh yes, it will also be good because using ARM core you can also reach full line rate. So uh, because for the ARM core, so for the RISC-V, the DPA it do not have operating system, so you can't just realize the most traditional algorithm directly on it. But for the ARM core, it runs a Linux system, so you can just have loads of tools that can help you to realize some like tiny ML or some efficient ML solutions that optimized for this.
But
Or I can treat it as edge-based solution.
yeah, yeah. But then regarding the latency, then I mean, like, if do you think does it affect if running on the Linux on the ARM cores?
Well, it affects, but it will not affect so much. So, according to a paper, if my memory is correct, so the latency effect, like if we use the DPA as a client and DPA as a server, the latency is definitely the slowest, the best latency performance. And if we use the host as a client and the host as a server, the latency is higher, but not that much.
Okay.
And similar to ARM and ARM to ARM core. So if we treat it as a server connected Bluefield 3 and link to another Bluefield 3 connected by a server. So under these scenarios, definitely the DPA have a lowest DPA to DPA have a lowest latency. But if we run some complex algorithm, then this reduced latency is not that significant.
Thank you very much. Thanks.
Yes.
Is there any other questions?
Yes.
Yes, so there is one more question, please. Yes, please. But I think that we cannot. I don't know. I see that Tariq, you raise your hand. I don't know. This is you have any questions? Yes. We cannot hear you. I don't know. This is
Yeah, probably there's something.
I think there's
Something with.
I think you are muted. Probably that's why.
What about now?
Yes, now it's yes. Now we can hear you. Please.
Now you can hear me.
Yes, yes.
Because I cannot hear myself. That's a good. Sorry for that, but it's a new tool for me as well. So thank you first for a great presentation. And since you are very active in the field, I got surprised, as many of us, when Intel discontinued Tofino in 2 years ago. So I would just like to hear your opinion on where is the programmable networking going. I have impression it's a little bit kind of cooled in research, while, for instance, smart NICs are on the rise. So do you have like unrelated to this research on a higher level, what is your opinion about the future of programmable network devices and also their application in practice? Do you think this will become mainstream at any point?
Thank you.
Yes. Thanks for the question. It's a really good question. Well, I think yes, the Tofino is already end of its life. Well, we still see the Pensando and the new Intel IPU, which also supports the P4. And as far as my experience, for some other network or self, because I'm now with Alibaba Cloud, and their IP is CIPU, if my memory is correct, is also P4 supported. So although like the Tofino is already EOL, I think the programmable network, this idea is still emerging. And the P4, although it's not that highly appear in research paper like in SIGCOMM or SDI, it's still already become a de facto tool and programming language inside the network. And for the future network devices, there are still will be a high portion of them support P4, although probably they will also support C or other programming method, but P4 is still will still exist.
Thank you.
Thank you. And Changgang, may I ask also one more question? So, you think that between these programmable network devices, which one is more promising? So, you think that maybe the direction goes more through the smart NIC or like the programmable switch?
It's really hard to say it, because like the smart NIC, definitely it is promising, because as we can see, that those cloud providers purchase huge amount of them, like Bluetooth 3. And for example, for their virtual private cloud, they depend on those like smart NIC or DPU that runs their virtual switch on it, so that they can just sell their bare metal or the VMs or ECS, Elastic Computing Service. Well, for switch, they are deployed at different locations, and they are also required. For example, like AI clusters for their backend network. So if we do not want to use a smart NIC as a backend NIC, so it need to use a smart or programmable switch to support some complex functions like isolations, like ACL, and other functionality that with the help of the programmable switch. So it has different locations inside the data center. So I think programmability in both components are very useful, but it should be used under different scenarios.
Thank you very much. Is there any other questions? So if not, so I can stop recording.